Okay, so welcome back, everyone. Before we begin today, would anybody like to ask me anything? No. Good. So I just very quickly want to show you two handy things that have to do with arrays, and then we'll move on. So last class we saw these arrays / lists, and we saw that there's a bunch of different methods that you can apply to an array or a list. Like you can ask them to sort themselves, for example, and then that sorts them, and I think you can ask them to reverse themselves, and that reverses them. I'd like to show you that there's two other ways of doing those same things without destroying the original array. So here's our original list. It contains 1, 2, 3, 4, 5 elements. And if I would like to have that thing reversed, then I can do so just by calling the reverse method, reversed function, which gives me something weird looking that looks like some kind of object. But if I convert that object into a list, it's the original list reversed. And the nice thing about it is that it doesn't destroy the original list. So I still have the original list A, which contained the elements in the usual order, and I also have this reversed version of it. And you don't always have to convert it into a list. Very often the only reason you're reversing it is because you want to iterate over it backwards, and that lets you do it like this. So I can say for x in reversed A, print x, and that does this iteration. X takes on each of the values in the list A, but starting with the last value first. Okay, it's a sort of handy thing. And similar to reversed, there is sorted, which gives you a sorted version of the original list. Now the sorting happens, in this case, if the list contains strings, then they're sorted in I'll say alphabetical order, but it's actually a little bit more sophisticated than that because upper and lowercase make a difference. They're sorted in the usual order you would get when you sort strings. Let's leave it at that. Okay. So sort of a couple of handy things to be able to do on lists. And the nice thing is sorted and reverse don't only work on lists, but they also work on other things. In fact, they work on anything that makes a sequence, and so in particular they also work on strings. So. I think this works. No. So you can iterate over the characters in a string in reverse order by calling this reversed method. The other thing you can do with a string is you can sort it. So let's remember this is my original string. So what do you think happens when you sort a string? So by analogy, lists and strings are kind of the same, they're kind of similar in that they have these individual elements and they're indexed starting from 0, 1, 2, 3, and so on. So when I sort a list, what happens is the list elements come out in sorted order, and when I sort a string, what happens is the characters come out in sorted order. So you get an array or a list that contains each of the individual characters of the string, and they're in this sorted string order, so all of the spaces come first, then the capital letter T, because all the capital letters come before all the lowercase letters, and then all the lowercase letters come out in alphabetical order. Okay. So those two things are handy, but they're sort of to do with the previous lecture. And now today we've reached a nice point. It's lecture number 4. We've reached a point where we will finally finish looking at the fundamental things in Python that make it a real, what we call Turing-complete programming language. So far we've seen, yes?
I'm just curious, are they sorted by their ASCII?
They're sorted by their ASCII values, yeah. Yeah, so we've seen numbers, we've seen strings, we have seen lists/arrays, and we've seen how you can iterate over lists and arrays. And we can do a lot of things with that, and we've seen little tricks like where you can multiply a string or a list by an integer, and then that kind of duplicates it many times, so you can get really big things. And then you can iterate over it, so that could mean you get a long iteration. But we haven't quite seen enough to make a complete language yet. In particular, we haven't seen anything yet that would allow us to write a program that runs forever. Right? What could we do? Well, all we can really do now is make big arrays and maybe even make them huge, and then iterate over them, but eventually that stops. And real programming languages allow you to write programs that can run forever if you need to, sometimes on purpose, sometimes by accident. And so today we're gonna see the last few pieces that we need to make a real programming language this way. And it's the last 2 control structures. We will see if statements, if then else statements, and we'll also see while loops. So these are these unbounded loops that allow you to write things that run forever. Okay. So let's start with if statements, and let's start with an easy example. Okay, so I want to write a function which takes an argument x and returns its absolute value. Can someone remind me what the absolute value of a number is? Yep. So it's the positive part of the number. And another way of saying that is, well, if the number is positive, then it's just the number itself. And if the number is negative, then you take away the negative sign, or if you like, you negate it, which is the same thing as taking away the negative sign. And if you just listened to me, you'll realize that I defined that, and I used the word if when I defined it. If the number is positive, you do one thing, and if the number is negative, you do something else. In particular, if the number is positive, there's nothing really interesting to do. The number is already its own absolute value. It's when the number is negative that we care about. Okay? So Python and just about every other programming language has control statements that allow you to test conditions like this and only execute some particular piece of code if the condition is true. So in our case, the condition is x less than 0? That's what it means to be a negative number. It means you're less than 0. And if that's true, then we want to do something special. Okay? And what is it that we want to do? Well, we want to give it its positive version, and an easy way to do that is just to say x is equal to minus x. So if the number is negative, for example, if it's minus 3, then minus minus 3 is just 3. Okay. And if that's not true, or whether or not that was true, now we can return the value of x. If x was positive, nothing happens. We just return the value of x. If x was negative, then we first negate it, and then we return it, and so we're returning a positive value. Okay. Is that clear? So let's test that. So my ABS 3 returns 3. My ABS minus 7 returns 7. Also works with floating point values. In fact, it works with anything you can compare to 0 and anything you can negate. All right. Is that clear? Yep.
Can you just put a negative on the right side of the equality? In Python that reads it as multiplying by negative.
Putting a negative is like multiplying by negative 1. Just putting a negative in front of a number negates it, sort of the way you would do in mathematics. So it's like it's called the unary negation operator. Unary meaning it has only one argument, which is the thing on its right side.
So if you were to go, instead of writing negative x, if you were to go x asterisk bracket negative 1 or parentheses, that's just redundant.
Yep, you could do this. There's many ways to write this thing. So if you don't like negative x, you could say minus 1 times x. But notice even to say that, we, in some sense, did the same thing because we have the number 1 and we put a negative sign in front of it, meaning we negated it. So Python lets you do that whether it's a literal number like 1 or whether it's a variable. Okay. It's using the negation operator. And if you don't like that, then you could also have done 0 minus x, which is the same thing as minus x. Lots of different ways to do it. This is, for somebody who does a lot of mathematics, putting a negative sign in front of something is a fairly standard notation. Okay. That's good. Let's try another one. Let's try okay. So if I want to return the maximum value of two numbers, so notice these functions I'm calling my ABS and my max. That's because the functions ABS and max already exist in Python. So I just want to see how you might implement these if you had to do them yourself. So I have two numbers, x and y, and I would like to return the maximum of the two values. So what's the condition that I should test? Yep. Yeah. So if x is bigger than y, then what should I be returning? Then I should return x. And if y is bigger than x, then I should return y. So now if I say my max 3 and 5, then I get 5. If I say my max 8 and 2, then I get 8. Okay. As I should. Now, let's go back to this code a bit. There are many ways we could have written this my max function. So there's one obvious thing that we could do here, and that is, if we look at the first two lines, it says if x is bigger than y, return x. Okay? Well, actually, no, let's pause for a second. This function is not correct. Is there a problem? Yeah. Yes. So let's check that. Then nothing gets returned. Okay, so this function is actually incorrect. So we need to deal with that edge case, and it's incorrect because it's a bit wordier than necessary. So the first two lines say if x is bigger than y, then return x. That's definitely the right thing to do, right? If x is the larger of the two, strictly the larger of the two, then I should return x. Now, remember, I've mentioned this, but you've not really seen very long functions yet, so this probably didn't sink in. When you call return inside a function, that's it. The function is over. That's in fact one of the main differences, or one of the several differences between return and print. Print will print something and keep going in the function. Return just leaves the function right at that point. So if we get to the next line over here, we already know that x was not bigger than y, which means that x is less than or equal to y, which means at that point it's actually safe to return y. Either the two things are equal or y is bigger than x, and we can just do that. And check everything. 3 versus 5, 5 wins. 8 versus 4, 8 wins. And 8 versus 8, 8 wins. Okay. So there's a good version of the max function. All right. Let's travel back in time, or travel to a different discipline. So if anybody's ever had a job as an accountant or an auditor or any of these types of things, anybody who deals with finances, there's kind of an old school way, and it comes back a little bit to what you were asking about putting the minus in front of things. So it happens very often in financing and accounting that you come across with negative numbers, right? For example, if you're calculating, the profit you made in some transaction, well, maybe it actually cost you more than you took in which case you get a negative number. And what they tend to do when they write these things down in these big sheets is those minus signs sometimes get lost, and so they format them slightly differently. What they do is they write either brackets or parentheses around negative numbers. So rather than putting a minus sign in front, which can also be confused with a binary operator, and so that's somehow confusing, they put parentheses around them, which mathematically means nothing, but in the way they look at these things, that it matters. Okay, so let's do the same thing. We're going to return a string representation of x using parentheses to denote negative values. Okay. So if x is negative, maybe x is minus 3, then I want to return a string that has 3 enclosed in parentheses. And if x is positive, then I just return a string that has x the way it is. Okay, so how would I do that? Someone help me write this code. Yeah.
Well, you have to see if x is less than 0.
So what is the condition that we're checking? We're checking if x is negative, and that's if x is less than 0. And if x is less than 0, then what do we do? Okay. So we should read the documentation a bit carefully. So this is supposed to return a string representation of x. So if I just say x equals minus x, then if x was a number and I negate it, it's still a number. So I need to convert something into a string at some point. Yeah?
Quotation marks around -x and then bracket.
Okay. So, like how exactly?
X is equal to the double quotation.
Okay. Double quotation marks.
One on each side. And then that will return a string.
That will return a string, and what is the string that it will return? It'll return literally the string minus and the letter x, not the number that happened to be there. Yeah?
You could leave that, like take the string of that, and then go to the next line and print the string with the bracket. Go to the next line.
Okay.
Print.
Print?
A bracket.
No. Print?
Or return.
Return, yeah.
So string bracket.
String bracket.
Plus, and then str. Plus.
There we go. Very good. And now we've seen the pattern. If that's true, then this is the code that's going to execute. It's going to return that thing, and then the function is over. If that's not true, then the next line of code will execute. And that should just return a string representation of x, which I know is not negative, so it doesn't need to have anything fancy done to it. So indeed that works. Lots of ways we could have done that. One thing to keep in mind is code is reusable, so you can always, if you write a function that does something that's handy for you, then feel free to use it whenever it's handy. And we actually have done that already. In fact, there's sort of two clues. If you find yourself writing the same piece of code more than once or in many places, and especially if it's a non-trivial piece of code, then you should maybe think about whether that little bit of logic really is its own thing. And in this case, well, what did we do here? We said if x is less than 0, x equals minus x. We've already kind of done exactly the same thing up there. So if we want, and there's many ways we can do this. We could just take the minus here. That would be fine. Or we can also reuse the absolute value thing, which also will negate this thing and make it positive for us. Okay? So lots of different ways to write this code, including even the part where we create the string with the parentheses around it. We could have used string.format to do that as well. Okay, good. So So let's say we want to talk informally about someone's age. And so, like really young people, their exact age matters. But once you get into your 20s, then you're just kind of in your 20s. And once you get into your 30s, you're in your 30s, you're 30-something. In your 40s, maybe even 40-something. And once you're over 50, you're just old, right? And the assignment, too, has a question very much like this, but it has to do with time. So let's see how so this is somehow, there's a bunch of different cases. We care about being less than 20. We care about being between 20 and 30. We care about being between 30 and 40, 40 and 50, and then bigger than 50. So we should figure out how to handle those things. So the first thing we care about is being less than 20. So if your age is less than 20, then I would return just your age as a string. That kind of matters. There's a big difference between 13 and 17 or 13 and 19. In fact, it's the difference between being an adult, being able to vote, being able to drink and buy marijuana nowadays, and not being able to do that. So that's kind of important. Okay, so that's what we want to do if your age is less than 20. And if your age is not less than 20, meaning it's bigger than or equal to 20, then you might do something like, well, if it's bigger than or equal to 20, but it's less than 30, then you maybe say something like return 20 something. Otherwise, if your age is between 30 but not less than 40, then you might return 30 something. If n is less than 50, you might return 40 something. And if your age is bigger than 50, then it will return old. Okay? So let's take a look at that and then see maybe there's nicer ways to write this. So 22 is 20-something. 14 is just 14. 35 is 30-something. 55 is old. So it seems to work. And so this nice bunch of things that's happening here. I will let you in on a sort of secret, which is there's a whole school of people who, when they write code and they write functions like this, they think it's important to have exactly one place where you return, and should somehow be at the end of the function, and so just exactly one place where you return. And here we're really pushing that. Here we have like 5 return statements inside this function. Maybe we can reduce that. Yeah?
In my logic, I made a mistake where I thought, why doesn't it, let's say the
Yep.
Why don't all the other if statements apply to n?
Okay.
So print everything up to...
Yeah. So this is where we've been using we've been using a couple of things, and maybe why we should rethink this in a way that makes it less confusing. But the first thing we're using is the fact that these things are evaluated in order. Okay. And the first time one of these things applies, we're done, we return. So none of the other stuff gets executed. So for example, if n is 44, n is not less than 20, so nothing interesting happens there. N is not less than 30, so nothing interesting happens there. N is not less than 40, nothing interesting happens there. But n is less than 50. And at that point, it returns 40-something. It doesn't return any of those preceding things because none of them applied, and it doesn't do any of the things that come after that because it's already returned at that point. Okay. Yeah.
Is there a way to make a compound if statement? For example, if n is less than 20 and some other thing?
Yes. Oh, there's a way to make compound if statements. We'll see those shortly. But for now, I'd like to rethink what we've done here. And instead of returning everywhere like this, let's just figure out what to do and what it is we should be returning, and then just return it at the end. So we're going to define something. Let's call it S. That's the thing we're going to return. And instead of returning everywhere here, we'll set S to the thing we want to return. And let's look again at these cases here. Really only one of these applies, right? Okay. So if n is less than 20, then we know what to do. If n is not less than 20, we should worry about the rest of it. Okay. So there's this way of stringing these things together in Python, which is if, elif, and finally else. It looks like this. Okay. So if I have a long list of things which are mutually exclusive cases, only one of which should apply, then I use this construct which is an if, a bunch of elifs, and then finally an else. And it works like this. You know, the if thing does exactly what you'd expect. If n is less than 20, then it sets that string s to the string representation of n. The elif says, well, if that preceding thing was not true, then consider this next condition. And this next condition is n is less than 30. If that's true, then set this thing to 20-something. And then the next one says, well, if that preceding thing wasn't true, but n is less than 40, then set it to 30-something. And the next one says, if the preceding thing wasn't true, and n is less than 50, set it to 40-something, rather. And the last one, the one which says else, says, if none of the above is true, then this is what you should do. Okay? So none of those preceding conditions was true. N was not less than 20, it was not less than 30, it was not less than 40, it was not less than 50. I can deduce myself now that that means n is bigger than or equal to 50, and so it's going to do that last thing. And I don't want to return here, I want to stick with what I've been doing. Set s equal to old. So this is a really common sort of pattern when you have something like, often it's a numeric value, and you want to break it up into categories. You can do that with this chain of if, elif things done exactly in this way. Okay, so let's do. Okay, is that clear? And the sort of shortest version of this kind of thing is when you skip out, you leave out all of the elifs, and you just have an if and an else, and that's the thing that looks like this. So I could have written the absolute value function. I could have written it in a different way. If x is less than 0, x gets minus x, or I could have just said, if I'm one of those people who's fussy about only returning once, then I could say something like the return value minus x, otherwise the return value should be x, and then finally return the return value. Some of you may prefer to program things this way. It can be helpful because it sometimes means that the person who's reading your code doesn't have to, it's easier for them to quickly understand what's happening. And it also, this way of doing things also ensures that you didn't leave any gaps. Like, for example, when we first did the max function, we actually had a gap there where x and y were equal and we weren't returning anything. If I do this with, if I do that with ifs and else, then I know one of the two things has to happen, right? Either if it's true, we do one thing, else we do some other thing. At least one of the two things has to happen, so we know that we've covered something. And in particular, in this example, we know that this variable retval will be set by the time we come to this return statement, which returns it. Okay? So, any questions about that? Clear? So this format 8 is a good guide for one of the questions on the assignment, maybe even more than one of them. Okay, so one of you asked me, can you combine these things, these comparisons with other in ways so that you can check if two of them are true at the same time? And the answer is yes. So let's write a function called is 20 something. When all I want to do is check if somebody is 20 or older and less than 30. Okay, so someone gives me a number n, and I want to know if it's bigger than or equal to 20, and it is less than 30. All right. So I've just said exactly what the condition is there, right? Is n bigger than or equal to 20, and is n less than 30? So we can just write that in Python. Is n bigger than or equal to 20, and n is less than 30. We can return true. Otherwise, we can return false. Okay. And if you've programmed in other languages before, this may look weird to you. The way you specify two conditions like that and you connect them with an and is you literally write the word and. In other languages, you might see ampersands, double ampersands, any of those things. Here, it's literally the word and. Okay? So, so 55 is not 20-something. 13 is not 20-something. But 25 is 20-something because it's bigger than or equal to 20 and it's less than 30. Yep.
So this, when you say return true, return false, these aren't strings, these are Boolean outputs.
Yeah. So something that we have seen in, what we've seen so far, and we've kind of seen these things, but we've kind of glossed over them. We've seen numbers, strings, lists, and we've kind of seen these Boolean values that come back when you do comparisons, right? So if I say 2 is less than 3, the less than operator is a binary operator that compares two numbers, and it returns true if the first one is, the one on the left side is smaller than the one on the right side, and it returns, it evaluates to false otherwise. Okay? And actually, we saw that right in the first class, we saw this order of operations. Brackets, exponentiation, division and multiplication, addition and subtraction. Those are the standard ones you've seen in high school. But then there was an even lower level, which was, I'll call it C for comparisons, right? Because we can ask questions like, 2 plus 3 is less than 6. And that comes back as true because 2 plus 3, the addition is done before we, on the left side of the less than operator, gets done before we do the comparison. So that includes things like, is 7 less than 6 plus 2? Yes. And implicitly that means that something weird is there's some grouping or ordering of operations happening because 6 plus 2 had to have been done before the comparison, because otherwise we'd be comparing 7 and 6. There's another reason that it had to have been done, because otherwise we would be comparing 7 and 6 and getting the answer false and then adding 2, which really doesn't make a ton of sense. So there's that. But now there's a whole other kind of operators that we have, which includes this AND operator. Okay? And that thing is at like the lowest possible level of operations. Because remember, comparisons were at the lowest before, and it looks like, if we look at this expression here, well, we check if n is bigger than or equal to 20. That gives us true or false. We check if n is less than 30. That gives us true or false. And this AND operation combines those two logical values. And the way AND works is the only time it returns true is if the thing on the left is true and the thing on the right is true. If either the thing on the left or the thing on the right or both of them are false, then AND gives you false. Okay? So this BEDMAS rule is actually extended with an even lower level of operations, which is these logical operations that include AND. Okay? So we can test this out, right? So we've decided now that there's these variables or these Boolean objects true and false. So I can ask you, true and true, what is that? That's true. True and false, that's false. So this AND operator only gives you back true if both its arguments are true. Yeah?
Is there an OR operator as well?
Yes. So there's also an OR operator. And what do you think, when do you think it gives you back the value true? It gives you back true when one of its arguments is true or both of its arguments are true. But if they're both false, that's the only time that it'll give you back false. And we can check that. We can say false or true. Indeed, that's true. False or false. That's false. True or true. And true or false. Okay. And this is one of these strange things in computer science. This kind of thing, writing false or true, true or false, that confuses people. And that confuses people more than expressions like this. When you write, n is less than or equal to 20, and n is bigger than or equal to 20, and n is less than 30. Somehow that makes more sense. It's a really concrete thing. You know what the test is, and you know when that's going to be true. But when you replace those things with logical values, it sometimes confuses people. But really what's happening is the expression on the left gets converted to true or false. Either it's true or it's not. And the one on the right, n is less than 30, gets converted to true or false. And then the operator AND decides, gives its output based on those two things. Good. And if you ever take a course in logic, you'll realize there's all kinds of manipulations that you can do to these things, where you can switch AND and OR by negating the various things to them and negating the whole result. So to be between 20 and 30, that's something like, well, here's another possibility. I could say if n is less than 20, then that's definitely not 20-something. Or if n is bigger than or equal to 30, then that's definitely not 20-something. Otherwise, you're 20-something, right? If you're less than 20, you're not 20-something. Or if you're bigger than or equal to 30, you're not 20-something. But if you're neither of those two things, then you're 20-something. Okay. So this is a really, talking about this in a very natural way like this makes sense to people, and people understand it. But what this is really doing, and if you're a computer science student, you know this. If you take philosophy of logic, you'll see this too. You're using something called De Morgan's law to express the same thing, a conjunction that uses AND as a disjunction that uses OR instead. And if you've ever done this before, this is this thing where you put two bars on top of this thing, saying you negate it twice, and then you manage to pull one of the bars inside and switch the AND for an OR. Okay. That can be extremely confusing to people, but I think when you talk about concrete examples like this, it makes sense. Okay. And so let's look at a couple more of these things. So we got any arrays here? No, let's make an array. So we've seen some of this before. We used this actually when we were looking for anagrams or anonyms. And we can ask questions of lists and arrays. We can ask things like, is 23, the number 23, is that contained in the list A? Well, the list A contains a bunch of strings. I don't see any numbers in there, so 23 is not in there. That's false. So that also gives us another one of these logical values that we can do things with. On the other hand, if I ask you, is B in that list? It returns true because B is there. It's the 1th element in the list. And sometimes you would like to, sometimes it's handy to have that value, and sometimes to know if it's in the list. Sometimes you want to know if it's not in the list. And there's another logical operation you can use, which is the not operation. So B is in A, that's true, but not B in A negates that, that's false. And Python weirdly did some stuff that I don't actually like so much, but somebody decided it should look more like English, and so you can also write, is B not in A? That's false, because B is in A. Is 23 not in A? That's true, 23 is not in A. So you can do that too. I find that a little confusing, but it works. Yeah.
If you did not be in A, would you do true?
Okay. Like this. Not. Yeah. So think of this not as that minus sign that we've been sticking in front of numbers, right? It negates it. It's a unary negation operator. So it takes one argument, the argument is on its right, and it just changes it from true to false or vice versa. Clear? Okay, good. All right. So now we've seen we can do branching, these if statements. That's good. But we're still not there. We still can't write a program that runs forever. For that, we need the sort of last big piece of the puzzle, the thing that is going to make this language Turing complete, and that's while loops. Okay? So a while loop is a loop, kind of like a for loop, but a for loop iterates over the values in some array or in some sequence. A while loop just says, as long as some condition is true, we're going to keep doing this block of code. So let's do an example. A really dumb one. So say start with I equal to 0, and then say while I is smaller than n, print I, and then say I equals I plus 1. Okay. So start with I equals 0, and then as long as I is smaller than n, we're going to print the value of I, and then we're going to increase the value of I. And indeed, if I call count 20, I print the values 0 through 19, right? Starting at 0, and this will continue as long as I is less than n. Now, the last time through this loop, I becomes n, I becomes 20, and this while statement says, okay, don't do it anymore now. So it doesn't do it for the value 20. Okay? And we can check that. Well, what happens after this loop is done? So indeed, once the loop is done executing, so once the stuff inside that while loop, the body of the while loop is done, the condition is no longer satisfied. So now I is not less than 20. It's actually equal to 20. We execute whatever comes after the loop. In this case, it's the print statement that tells us what that final value of I was. Yep. What if I equals 1? You mean if I start with I equals 1 here? So what do you think is going to happen? It will stop. So what will get printed? Yep. Yeah. So it'll be, or my guess is, it will be exactly what you see here, this counter, including the last line, but that first line won't be missing, because I never took on the value 0, right? I started at 1, that's less than 20, so that'll execute and it'll print it, and then 2, and then 3, and then so on, all the way up to 20, which is not less than 20, so it won't print that, and then it'll go to the line that follows the while loop. And we can check that. Always remembering to reload. Starts at 1 and counts up to 19. So it's not enough if you were trying to count from 1 to 20. That's not enough. You do have to start at 1, but you also need to change the condition here to not say is I less than n, but is I less than or equal to n. Okay. And if we do that, then we get the expected result. Counts from 1 to 20, and then exits at the value 21. Okay? All right. So let's look at how we might use this for something that interacts with the user. So we want to read stuff that the user is typing in until the user enters a blank line, and then we want to stop. Okay. So that's the idea. So that means we'll need to read at least one line from the user, right? So maybe if we're going to do that, our function should maybe start with that. And so we'll say line is equal to input, and we'll put a funny looking prompt for the user to read things. Okay. So we're going to read that first line. And now we want to continue and read lines until the user enters a blank one. So this is a program, we don't know in advance how long it's going to run. That depends on the user. So we can't just use a for loop, because for that we would need a range or a list, and we'd need to know in advance how long this is going to happen. So the while loop is the thing to do here. So when we have a while loop, then we have to decide, well, what's the condition where we should continue, and what's the condition where we should stop? So in this case, when should we continue reading more lines from the user? Yep.
While the input does not equal null.
Yeah. So another way of saying that is, while the length of the line that I just read, well, that's bigger than 0, then I should read another line. that's what I do there. And then I stop when when the length of the line is equal to 0. So let's test that out. And indeed, the last one was the blank line, and it stopped and returned me back to the Python. So the function stopped. Yeah.
And you can also do like a exclamation mark equals and then empty quotes.
Yeah. So instead of asking for the length of the line, I could have said while the line is not equal to the empty string, that would accomplish the same thing. Does the same thing. There's a few ways to write that test. Okay. All right. Now let's do something slightly more ambitious, just to see a very common pattern. Read input lines until the user empties a blank line, and then return the concatenation of all the input. So that means not only do we want to read these things, but we want to store them, save them up, and then return the whole thing at the end. Okay. And for that, we can use a common pattern which they call an accumulator. It's a common thing when you're trying to add up things or put things together. So there's a few ways we could do it. We could say the following. Let's create a list, an empty list. And each time the user enters something, we append it to the list. And then finally, when we're done, we want to return, well, it's not the list that we want to return, but we want to return all the strings that are in that list all glued together. And we've seen something that does that. Right, we have a list of strings now. Glue them all together and return that. See if that works. Oops. So that glues them all together. And here we have to be it's actually quite delicate, right? So we got to make sure we catch all the lines that the user entered, not missing any, including that first one that happened on top. And luckily for us, we're using the fact that the last one is empty. So whether we concatenate it or not is not going to make a difference. Because if you look here, that last one, which was empty, never gets added to the list A. But it doesn't matter because it's an empty string, so we wouldn't, whether we include it at the end or not, doesn't matter. Okay? So you have to think these things through quite carefully. All right. So let's jump, yes?
I want to ask about A equals square brackets. If you were to put that in the it's an array that's open for anything, or do you have to define the array beforehand?
No, that means that it's an empty list. Yep. Oh, that's because you can't see it, but that's because I hit space before pressing enter. Yeah. If you wanted spaces between all of them, then over here in the join, you could put that, and now it's going to put a space between each array element. Depends what exactly you want out of this. Yep. An exclamation mark here. So there's these comparison operators, less than, bigger than, less than or equal to, bigger than or equal to, and there's equal to, which is denoted by two equal signs, and then there's not equal to. And you've probably seen this in mathematics. This means A is not equal to B, and computer programming, that's kind of the cheap way of trying to simulate that, because we don't have a not equal to symbol in ASCII, or at least not one that we can get to with our keyboard very easily. But the other thing to look out for is this returns true if A equals B. This is different. This sets A to the value B. So these two things are not equal. Okay. So jumping from computer science now to, let's say, modern mathematics, I would like to talk to you about a problem which is open. It's a mathematical problem, and it's been open for a long, long time. It's a very difficult problem. A very famous mathematician named Paul Erdős commented about this problem. He basically said, mathematics isn't yet ready to study these kinds of problems. And it's called the Collatz Conjecture, and it's very easy to state. It's one that I like. It's really easy to explain. And it's actually really easy to use as an example here, because we can test the conjecture a whole bunch of times writing a simple program like this, so really contribute to modern mathematics. But we'll never, I doubt anybody in this classroom will solve the problem, but it's still fun to play with. So the conjecture is really easy. It says you start with any integer, positive integer. So maybe you start with the integer 7. And if that integer is odd, then you multiply it by 3 and add 1. So 7 times 3 is 21, and if I add 1, it's 22. On the other hand, if the integer is even, then you just divide it by 2. Okay? So my 7 multiplied by 3 plus 1 is 22, but that number is even, so I divide it by 2, gives me 11. That number is odd, so I should multiply it by 3 and add 1. So that's 33 plus 1 is 34. That number is even, so I should divide it by 2, which is 17. 17 is odd, so I should multiply it by 3 and add 1. And we continue this way. And we'll stop if we ever get down to the number 1. Otherwise, we'll continue forever. Now, do you think this will stop, or do you think it will continue forever? It's hard to say, right? We start with some smallish number, 7 in this case. It's odd, and we multiply it by 3. That's kind of a big blow up. And we add 1. And now we know that that one is even, so the next thing we're going to do for sure is divide by 2, but I don't know what I'm at now. Is that even or odd? It was an even number, I divided it by 2. It might still be even, it might not be. But if I keep, dividing by 2 and then multiplying by 3 and adding 1, just alternating those two things, for sure that's just going to grow off to infinity. But sometimes I get to divide by 2 twice in a row or 3 times in a row or whatever. So the Collatz conjecture says that no matter which number you start with, this process always ends and brings you back to 1. So we can test that. Let's write a function called Collatz. It takes the integer n, and it does exactly this. Okay? So, this is a process that is supposed to continue until the value of n is equal to 1. All right? So, we don't know if it goes on forever or not. So that kind of means we need a while loop because there's a possibility that it could go on forever. So we got a while loop. And when's that while loop going to stop? Well, the problem statement says you should stop when you reach the value of 1. So while n is, let's say, bigger than 1, we'll continue. And now there's sort of two things you can do with n, depending on whether it's even or odd. Okay? So I will just write this, but you're going to have to tell me how to do it properly. If n is even, then we say n is equal to n divided by 2. And I'm using div here because I want integer division. I know it's even. If I divide it by 2, there's no remainder. I don't want to accidentally get a floating point number here because this is a problem on integers. Otherwise, if n is odd, then n is equal to 3 times n plus 1. Okay? Now, this is not quite done yet. If n is even, how do I express that? This is not something that's valid Python right now. How do I express if n is even? Yep. If what's that? Don't need to input math. Yeah.
The remainder should be 0?
The remainder after dividing by 2. So the way to get the remainder after dividing by 2, that's n mod 2. That should be equal to 0. So let's put that there. Some people will forget. Tests if n is even. All right. Okay, that wasn't very informative. So I did Collatz 50, and here I am. So what can you conclude about that value of n? Yeah?
Well, we didn't put if n is 1, so I guess that means that it reached 1.
Yes. So we have a while loop here that will continue as long as n is bigger than 1. So actually, even though I didn't see anything happen, the fact that this thing finished and sent me back here, it's not still running, means that the Collatz conjecture must be true for n equals 50. Now the Collatz conjecture, the real conjecture is it's true for every positive integer. There's an infinite number of those, unfortunately, so we're not going to be able to resolve it just using Python because we don't have an infinite amount of time to wait, but we've just verified it for n equals 50. Okay? And we can look at what the pattern is because we can print this thing. For example, let's look at So what happened when we did Collatz 50? Well, 50 was even, then we got 25, which was odd, 76, 38, 19, 58, 29, 88, 42, 22, 11, 34, 17, 52, and so on. 11 is one we actually saw earlier, so we could conclude even that the Collatz 7 that we started with, that's also going to finish because it reached 11 at some point. And this one finishes, the last number we printed was 2. That's because after we divide by 2, we get 1 and the thing exits. Okay. Good. So we can check it for some other number. I don't know, maybe 16. Is that a tough one? No. 16 is a power of 2. Every time we divide it, we get an even number until we get down to 1. Let's try it with 17. Still not tough. Let's try it with 500. Done quickly. 5,000. We can try it with, I don't know, some big number. That didn't take very long either. Well, I mean, taking a little random samples like this is fine, but, you know, let's do this systematically. Let's check everything. So how do we do that? Well, we'll want to write, so we'll get rid of the print because we already know this thing, if it returns, it's verified this conjecture. So let's say test Collatz. And we'll write our first infinite loop. And we'll say while true. We start with n equals 1. That one we already know is true, but let's do it anyway. This is an infinite loop. It's going to execute forever. And what we do is Collatz n. Now, if I run this now, what's going to happen? Am I going to learn anything by running this just the way it is? Yep.
No, because it's just going to keep adding numbers.
It's going to run forever, but I won't know if it's running forever because it's just the value of n is getting bigger and bigger, or if it's running forever because it got to a value of n that got stuck, where the conjecture wasn't true, and it's the Collatz function that's running forever, not the test Collatz function. So we better have some output here to see that this thing is actually progressing. So every time we verify it for a value of n, let's print. Oh, let me clean that up a little bit. This is this old typewriter trick that I mentioned in the past. So there it is, verifying the Collatz conjecture. It's now up to 200,000, 300,000, 400,000, 500,000. We'll be at 1 million in a couple of seconds. Yeah, so it indeed seems to be true for n up to 1 million. That is nothing like the largest values that it's known to be true for, but it's getting there. And so, you know, in this few lines of Python, in the couple of weeks that you've been in this course, you have the skills now that somebody can come along with a research problem in mathematics which is too difficult for mathematicians to solve, for sure nowadays, and you can write a few lines of code that will give super strong evidence about whether or not that thing is true or not. Okay. So those of you in the sciences, this means with Python you can very quickly test conjectures and about statistical questions, about mathematical questions, and give evidence about the answers of those things. Not necessarily solve them, because this won't solve it. This just says for all the values we've tested, it's been true. But it gives very, very strong evidence. And in some branches of science, that very, very strong evidence is actually enough to conclude things. Good place to leave it for today.